Anyway. So, we're going to start with something we're very familiar with, which is just we're going to describe the line in Cartesian form, and then we're going to look at two other alternative ways of describing a line, that is parametric form and vector form. So firstly, if we've got two sets of coordinates and we want to find the equation of the line that satisfies this, we'll get these fellas in as well. G'day guys, you merged with us today, so come on in, and if you just work quietly for the first sort of 20 minutes, that'd be good. Mrs. Much has put some stuff on sector. So. Okay, so for a line, for the equation of a line, we need slope. Okay, so remember y equals mx plus c. We need the slope, and slope is y2 take y1 on x2 take x1. So we just plug that in, 5 take 4, on top of 3 take away 2. We're going to have a slope of 1. So that means we have y equals x plus c, and then to determine the c value, the y-intercept, we can plug either coordinate in. Let's go with the first one. We've got when y is 4, x is 2. Which means the c value is 2. So the equation of this line, the Cartesian equation of this line, is y equals x plus 2. All right. So let's leave that there for now. That's the Cartesian equation. Let's look at how we can find the vector equation. Now the vector equation, what it's going to be a coordinate plus some variable multiplied by a direction vector. So that's going to be the parametric form for the equation of a line. So let's find the direction vector between these two coordinates. I'm going from this coordinate to this coordinate. I want to know the direction vector. All right, so the direction vector is just, it's going to be the vector that results when we go, you can think of it as like the vector from A to B is going to be the coordinates of B take the coordinates of A, right? So we'll have 3 take away 2. We have an x direction of 1, and 5 take away 4, a y direction of 1. And then we just choose a coordinate that it passes through, doesn't matter which one, we'll go through 2, 4, plus t times 1, 1. Now most frequently we'll use t. Every now and then when we have multiple lines, we'll throw in other variables like lambda and so forth. But this is the parametric equation of a line. So this describes the same relationship that this describes on a Cartesian plane. Okay, and then of course the vector equation. All right, all we do is we say, what's the x coordinate equal to for any value on this line? Well, it's going to equal this first coordinate plus t times our direction vector, so 2 plus t times 1, that's just 2 plus t. The x value is always 2 plus t, and the y value will always be 4 plus t. And so just like, you could have a table of values, all right? So you could find all of the coordinates on this line. So this is just an example. All right, when t is 0, the x value is 2, the y value is 4. We know it passes through that coordinate, right? When t is 1, the x value is 3, and the y value is 5. We know it passes through that coordinate as well. When t is 2, we have 4 and 6, etc., etc. So all of a sudden we have t describing, the variable t describing the location of the point on the line. Okay, so one more link to make. I just want to come over here and I want to talk about this slope 1. We have a slope of 1. Now, if we have a slope of 1, that means you always think about slope as change in y on change in x. So it's 1 on top of 1, right? So that means we're going across 1, up 1. And so you think this vector across 1, the change in x is 1, the change in y is 1. So you can see the link between slope and where we derive this vector from. Very good. So that's the first example. Let's move on to the second one. We have, consider the point minus 1 and 4. X is minus 1, y is 4. And we want to we're told a vector that's perpendicular to this line that we're trying to find, all right, has this direction. Okay, that's the direction of a perpendicular vector. So we want to go, what's a vector that's perpendicular to this? All right, so we should be thinking about dot product, and if we need some vector, direction vector AB, such that AB dot 3 minus 1 equals 0. That's going to give us a perpendicular vector, right? And look at this, we'll have 3A, take away B. I might think of it, instead of A and B, I'm going to use X and Y actually, here, sorry. We'll have 3X, take away Y, equals 0. And we can see this gives us Y equals 3X. Which means the vector perpendicular to this one has a slope of 3. All right. So that's going to be the slope of the vector through this point. So if we want the Cartesian equation, we're going to have y equals mx plus c. We've got the slope. And then in order to find the c value, we're just going to plug any coordinate in. This is the coordinate, this is the direction, so we're going to plug this one in. We've got y is 4, x is minus 1. And so we'll get c is positive 7. Okay, so that's the Cartesian equation, right? We're familiar with that. Let's look at both the parametric and the vector. Now remember, this direction vector is perpendicular. So the vector we're interested in has a slope of 3, okay? Again, 3 by itself is 3 on 1, and so that means x goes across 1 and up 3, all right? X goes across 1, y goes up 3. We've got our slope is 3. And if you were to plot both of these vectors, you'll see that they're perpendicular on the Cartesian plane. Let's just sketch one quickly. If we have across 3, down 1, so 1, 2, 3, and then down 1. So that's the line that results, okay? And we're comparing that with a line that goes across 1, up 3. So across 1, up 1, 2, 3, and that line, they're going to be 90 degrees. So this was the direction that we're given, across 3, down 1, and this is the direction we've found that is perpendicular to it. Okay, that's its direction. So we've got the direction of the perpendicular vector, so then parametric form is going to be the coordinate we pass through, plus our variable multiplied by our direction. So that's parametric form. And then vector form, we're just saying, what's the x value? The x value is going to be minus 1 plus t. And the y value, okay, we take the y coordinate, it's going to be 4 plus, and we have t times 3, 3t. All right, do you sort of recollect this from year 11 a bit? No, can't remember it, but does it look okay as a way of describing a line? Good, because we're going to move on from 2 dimensions then to 3 dimensions. Okay, so hopefully that's okay, and we'll have a look at it. Do you guys want to practice some 2-dimension ones first, or no? Happy with it? Cool. All right, so get to our next example then. We have, consider a line parallel to this vector. So if it's parallel to this vector, 1, 2, and minus 1, parallel means they have the same slope. They're going in the same direction, right? So these will be going in the same direction. Quick one. Excellent. Thank you. Thank you. Beautiful. Okay, so it's got this direction, and we're told it passes through the point. X is 4, y is 0, z is minus 2. Find this line in Cartesian form, parametric form, and vector form. Okay, so for parametric form, we'll start with that. And with vectors in 3 dimensions, parametric form and vector form tend to be the most common way we define them. Rarely we use Cartesian form, but we will go over it as well. So the parametric form, as we said before, is just a coordinate plus some variable multiplied by our direction. Okay? And that is going to describe a point in three-dimensional space, right? So when t is 0, it's at this coordinate. When t is 1, when we put 1 there, we're adding one lot of this to this, and that gives us a new x coordinate. Our x coordinate would be 5, our y coordinate would be 2, our z coordinate would be -3. So it describes points in space that lie in a straight line. Okay, so that's the parametric. Here's the vector. We would have x is 4 plus t. We would have y is 0 plus 2t. So we'll just write y is equal to 2t. And we would have z equals, we'll have -2 take away t. Okay, now the way we get the Cartesian form, all right? The way we get the Cartesian form for a three-dimensional line is a little bit more complex than 2 dimensions. What we're going to do is we'll take this x, right? We've got x equals 4 plus t, and we're just going to go x take away 4 divided by the coefficient of t. All right, so x take away the number, and then divided by the coefficient of t. And then we're going to make that equal to y take away the number. Our number here is 0, so I'm going to write it up just for the sake of demonstrating the process, the algorithm. So we have y take away 0, and then divided by the coefficient of t. And then we make that equal to z. Z take away the coordinate, so we'll have z take away -2. Divided by the coefficient of t is -1. So we have a relationship of equality because what we've basically done is solved for t, solved for t, solved for t, and make them equal to each other because t is a variable that's present in all three of these equations. So we'll just simplify that a bit. We'll have x take 4 is equal to y on top of 2, which is equal to, now that would be z plus 2, and then z plus 2 divided by -1 will be -z take away 2. All right, so that there is the Cartesian equation, and we rarely use the Cartesian equation. To go from the Cartesian equation back to here, all you're doing is setting each part equal to t and solving for x, y, and z. That will pop up. So let's talk about like these ways of describing the line, right? I think this is it's really clear the link between these two, okay? And so this, you can see, describes an x coordinate, like we have a set of coordinates in space. So if we have t, and then I can have x, y, z, and we know that the first point that it passes through, when t is 0, the point that it passes through is 4, 0, -2. And then we have when t is 1, all right, I'm choosing whole integer values here. When t is 1, we would have, let's do it from here. 4 plus 1, 5. 2 times 1, 2. -2 take 1, -3. So that would be the second coordinate that it passes through. All right. Let's get another coordinate when t is 2. So we'll have 4 plus 2. We would have 6, 4, and -4. And so they're just coordinates that this line is going to pass through, all right? And so a bit like when we plot them on the Cartesian plane, we go, oh yeah, passes through here, passes through here, passes through here, and then you can sketch a line through them. Obviously, it exists on every point between these lines, but for decimal values of t. Like we could go when t is 1/2, all right, it exists in between here, when t is 1/4, and so on, reducing to infinity. All right, that's our third example. Okay. Fourth one, determine the direction vector of the following lines. So all we want is what's its direction, which way is it going? We've got 3 lines described in different forms. So our first line is in parametric form, -1, 0, 2. Okay, that's the coordinate plus the variable multiplied by the direction. What's the direction it's going in? The direction vector is this one, minus 1, 0, 2. Sorry, we don't normally put coordinate columns there. Okay, for B, we have x equals 2 plus 3t, y equals t, and z equals 1. So if we were, like, let's think about how could I move from there back to here, okay? How could I move from vector form? I really want to draw out those relationships. How could I move from vector form back to parametric form? So the first thing we need is the coordinate. What are the coordinates that we're given? Well, here we've got 2. Here we don't have a coordinate, we've only got a t value, so 2, 0, and 1. And then we would have plus t multiplied by, well, which direction it's going. What do we have? We've got 3 lots of t there, we've got 1 lot of t there, and we've got 0 lots of t there. Okay, so the direction vector of this line, which is in vector form here, parametric form here, direction vector is 3, 1, 0. All we're doing is looking at what's the coefficients of t. Okay, but I'm just drawing out. So we'll answer the question. Direction vector 3, 1, 0. Okay. Last one. The question 4. Alright, so we have x take 1 on top of 2 equals y on top of 3 equals z. Cartesian form. Okay, we have a relationship between x, y, and z. So when it's presented in Cartesian form, all we do is equate each part of the equality with t. So we'll go x take 1 on 2 equals t, y on 3 equals t, and we have z equals t. Okay, solve through for x and y and z. Here we'll have x take 1 equals 2t, and we'll have x equals 1 plus 2t. Here we'll have y equals 3t, and we've got z equals t. So we have moved there from the Cartesian form to the vector form. We're told the x coordinate, the y coordinate, and the z coordinate, and we want to know what's the direction vector of this line. Okay, and they're just the coefficients of t. So we'll have 2, 3, 1. Now the other thing to point out is that corresponds with the denominators here, doesn't it? 2, 3, and 1. Now the only thing to watch out for, if you're just going to subtract those values from there, is they all have to be positive. Because we saw over here, I've rubbed it out now, but we had a negative value of z because we simplified it. So I think it makes more sense to equate them to t, observe the direction vector, and then hence state it. Okay, here we go. Find the equation of a line through 2 coordinates. Number 5. So we have the coordinate 4, 1, 0. I'm going to label them. I'm going to call them point A and point B. 2 minus 2, 2. Okay, first let's find it in, it just says find it in parametric form. Okay, so for parametric form, we have a coordinate plus a direction vector. Okay, plus t times the direction vector. So the coordinate A plus t times the direction from A to B. What's the direction we would take from A to B? Now we're very good at finding these vectors now. So we're just going to have the coordinate A plus the variable t, and the direction AB, the vector from A to B, we do the coordinates of B, take the coordinates of A. Dunsky. Okay, part B says determine 4 other coordinates that lie on this line. So we'll just choose a few different values of t. Four other sets of coordinates. So I'll put in first when t is 1, and you can do plus or minus 1, you can do plus or minus 2. doesn't matter. It's going in both directions aligned, right? A straight line goes infinitely both ways forever. So let's just go with t is 1. I'm going to have 4 plus 1 times minus 2. So 4 take away 2. That's positive 2. We have 1 take away 3. We'll have minus 2. And 0 plus 2, we'll have 2. All right. That's our B coordinate, isn't it? I mean, it does ask for 4 other coordinates, but I don't really mind. Let's just list these 4. So we've got the first one. Second one, when t is 2. All right, I think let's just solve them and I'll put them up here. We're pretty happy with the process. So we'll have 0. And then y. So down by 3. Z is down by 2 each time. 6, 8. Alright, so the fastest way to think about that, right, the fastest way to get heaps of coordinates out quickly is I'm just looking at how much is x changing by each time. It's going down by 2 each time. So I just went 2, 0, minus 2, minus 4. Y is going down by 3 each time, and Z is going up by 2 each time. Okay? Excellent. Now, part C says, determine where this line meets the xy plane. We're just going to change that to say xz, such that it's not one of the coordinates we have. I want to know, when does it meet the xz plane? Now, we've got an image sketch there that draws those out for you. We're familiar with variables x and y. Oh, they've sketched it a bit differently. I'll do the exact same thing that they've done. They've got y and z, just so we can refer to it. Y and z, okay, so the xy plane is the two-dimensional space made up of the axes x and y. The yz plane is the two-dimensional space made up of the axes y and z, and the xz plane. So I said, let's do xz. Let's find out, when does the line meet the xz plane? Now, what's going on when it meets the xz plane? This plane is the y value. The y value is 0, all right, because it has no depth along the y-axis. And so all you're doing then is finding what makes the y value. Our y value is 1, take away 3t. What makes the y value equal to 0? And so we'll solve for t. All right. Determine where this line meets the xyz plane. So that's the value of t where it meets it. Let's find the coordinates. Now I already know the y coordinate is 0 because that's where it meets the xz plane. That's when the y value is 0. So we just want the x value, which is going to be 4, take 2/3. So that's 3 1/3. And 0 plus 2/3. Very good. Okay, so this is all we're doing today. It's a really good exercise, beautiful ways of describing lines. They will start in 2 dimensions, okay, so you just have x and y, and then I think it moves on to 3. So let's give that a crack. I'm going to get each of you guys to